Now, as I keep doing every single time, just to sort of, pack this thing into a sensible chunk, just very, very quickly going to go through all the slides. This redox and feasibility, the redox bit we're almost finished on. This is the last bit of practical work for the course, really. Apart from your field trips, I think the last bit for chemistry and biology, we don't have any. From there, we then have this bit on feasibility to do, which is sort of the tail end, but we've really been looking at the idea of reactions being feasible, which direction they go in terms of an equilibrium, and whether it's actually feasible to consider that reactions are reversible. The reversibility idea is very much a theoretical idea, but we're actually going to be able to prove which sorts of reactions are feasible in relation to the energy, and it's the Gibbs free energy that I mentioned at the end of the energetics learning outcome. And I did a little PowerPoint that I don't think I gave you any information on that, because I said it was just a link through to other things we'd be doing, just to show that chemistry is not these separate things, but actually they are all interrelated. So the tail end of this bit, having done redox, oxidation and reduction, the flow of electrons, and working out these standard electrode potentials, then this is going to link back to the first learning outcome, because it will mention enthalpy to a small extent, because we've got that idea of enthalpy and entropy, haven't we? And it'll also link back to the equilibrium constant from the second learning outcome. So it's it's a nice way of sort of drawing the ends of it together, really. And the first year when I ran this unit after my colleague left, I had the learning outcomes in a different order, and I think I did rates and equilibrium at the end, and that it didn't seem right somehow, because the redox bit with the idea of equilibrium constant then didn't make any sense. But talking about equilibrium, this has led quite well into this, so it works, you see. It's like I know what I'm doing. So where have we been? Well, if you need to go back to any of this to help you get through the assignment, then it's all there. I will actually convert this to PowerPoint, and not PowerPoint, PDF, and put it on Moodle once we're done with it this afternoon. And I'll make sure that the PowerPoint is on there as well, and then there should be a full set of YouTube videos for the whole learning outcome too. Right, so we started looking at this idea of ionic equations and the movement of electrons, and the fact that not everything is involved. So we had this idea of spectator ions, because they're important this afternoon. We defined oxidation and reduction in terms of oxygen, hydrogen and electrons, the electrons being the important bit here, remembering that if one substance is reduced, then something else has to be oxidized. We had this bit, the oxidation states or oxidation numbers. You've got rules for working them out, and when I was talking through the assignment yesterday, that first part of the assignment where you've got to identify the oxidation number of nitrogen in two formulae, you just need to go through these rules and work out, explain why it is you're allocating certain oxidation numbers. So that is, where the material is for that first bit of the question. We went on to some examples. I seem to remember the sound failing on that one, but the answers are there. Having got the definition for oxidation numbers, we then started to look at oxidation and reduction in terms of those, and moved on to the idea of different reactivity. You can look at it in terms of change of oxidation number, but this was almost a separate section, because what we were looking at was the idea that some metals give up their electrons more easily than others, and the way this then developed was into a reactivity series, or the electrochemical series is a much bigger version of this, which is about comparing the position of equilibrium, and that was the order that they were going to come in, where the ones at the top had their equilibrium much further to the left than those at the bottom. Yeah, so the ones at the top are much more likely to exist as ions and electrons than the ones at the bottom. So if you were to put, and this, this is what you can read from this, if you put a piece of magnesium into a solution of copper ions, then the magnesium would rather be ions than the copper would, so they will change places. You get a displacement so that the magnesium goes into solution and the copper comes out. The other way around, if you put copper into magnesium ions, they'll stay as they are. And so on. So we started looking at that, and then we've developed this a lot further into redox equations, and this got very elaborate. That one I had to come back to, didn't I, because I couldn't do it on the spot, but all was solved in the end, but it did get rather lengthy. We then looked at specific examples of redox equations and how to create them from information that you're given, breaking it into half reactions, balancing for atoms, balancing for oxygen, balancing for hydrogen, balancing for electrons, and then multiplying up as necessary, adding the two together, cancelling out on each side, and way, Bob's your uncle, as they say. There you go, a redox equation. And so we had quite a few of those, and yeah, we played with those for quite some time. Right, now I think that then led me to give you the assignment question to have a look at. So I think people had started that. The layout obviously is where you can sort of gain extra credit on that one. And then, yeah, this was last week still, I think, wasn't it? The idea of electrochemical cells. And we started off with just this idea of sticking a piece of metal into water and the fact that you will get metal becoming ions into the water, leaving electrons behind. And what we were doing here was making this comparison between two metals and this idea of the equilibria again. And that's all this is about, is comparing equilibria. And it's the comparison here, and this got repeated over and over and over again. So, you should be hearing this in your sleep, that the position of the equilibrium for magnesium is further to the left than the copper one. So in other words, magnesium gives up electrons more readily than copper does. The doing it like that, those are just sort of half cells, can't do anything with them, and we can't actually measure anything there either. The only way we can measure the difference in the number of electrons is to use this reference electrode, which we don't use. We don't have one. We don't do this. But we, all the values that we get for electrode potentials are in comparison with hydrogen. We say hydrogen is 0, and we compare everything else to that. So we had, for example, the, comparing a copper electrode to hydrogen, and it would be set up like that. So that's our overall setup, which is pretty much how things are going to be set up this afternoon, but not with a hydrogen electrode, using the different metals. The assumptions, remember, pressure 100 kilopascals, although the old measure was 101.3. The pressure today, I believe, is about 101.6. So, we're not going to be very far off. The temperature I haven't checked, but yeah, 25 degrees, we weren't far off that yesterday. And then the solutions will be at 1 mole per decimeter cubed. So, we're doing this in standard conditions. We then started looking at the numbers, and in comparison with hydrogen, you then have all these different standard electrode potentials, E0. And those, of course, you get out of the data book. You can't measure it for one directly unless you're comparing against a hydrogen electrode. So what you're going to be doing is measuring the overall voltage of a cell when you actually connect two of these up, and then you're going to use those values to work out what it should be, and it will be way off for two of them and should be almost spot on for the other one. So this setup between magnesium and copper, I think I built that one up gradually to just explain the parts of it, things like the voltmeter and the salt bridge in there, so they're going to be part of what you do later. And then, yeah, I kept going back and recapping, so it was always going to be about magnesium, although that's the one that's going to cause us the problems this afternoon. We know this. And that was just recap bit. We then, oh yeah, we did the bit on cell conventions, how to draw or write a cell using the standard sort of setup with a vertical line, single vertical lines between the phasers in one half cell, and then double vertical lines to indicate the salt bridge. And yeah, I had a, a bit of an issue with my arrow there. And then, was this yesterday? Must have been, I think. We started joining it all up, joining up half cells to make whole cells, where if we've got two metals in solutions of their ions, connected by a voltmeter, but with a salt bridge allowing movement of electrons to complete the circuit in between them, we are then looking at a comparison of the sort of electron pressure, if you like, on either side there. And what the voltmeter reads, we should be able to calculate from the standard electrode potentials in the data book. So we were looking at this, and the difference between the standard electrode potentials would give us, hopefully, what you'd be able to read off on the voltmeter. Ha ha. And if you write them out so that the smallest electrode potential is at the top, all right, now that may be the more negative, or it may be the least positive, like that. Then if you write them like this, your two equilibria, then you apply the clockwise rule, which tells you which direction the equilibria will actually go in. So the one that has got the greatest negativity or the least positivity will go from right to left, where the metal will become ions and leave the electrons behind, whereas the other one will go the other way, come out of solution maybe, and turn into the metal itself. The standard sort of way to actually represent it, you would use, you can use sort of axes to do this. And so we looked at some examples. We did a lead copper example, laying it out like that. And was that about the end of it? It was, wasn't it? Right. So at that point, what I was going to do was say, right, now do the practicals for that and do the calculations, and then I would have to stop you, and you'd all be at different places. So it doesn't really work like that. So what I am going to do is to finish off the last bit on this. Hopefully this won't take us more than, oh, I have no idea. Now we've got it actually on a PowerPoint, it shouldn't be too bad at all. You can keep referring back to that. But, this should be well out of the way. I have no idea how long it takes. Might only take half an hour. We'll see. Then you can do the practical work. That seriously doesn't take long. And then all you've got to do is the calculations and write it all up. And chemistry is done. So, yeah, this last bit then, it seems odd not putting anything on the smartboard actually, but I don't really need that, so let's park that for now. I just want to go back to this. Now, I can't remember whether I put that onto Moodle. If I did, I may well have put it in a not very appropriate place, so I will make sure before the end of this afternoon that I've put that somewhere where you can refer to it if you want to. But it was when we got to the end of the energetics section, the idea of enthalpy, that I felt we were really short-changing it a bit, not really talking about thermodynamics properly. Not that, I can, time just doesn't allow us to explore every nook and cranny of it. But I wanted to just introduce a couple of other ideas at that point that I would be coming back to, because it related to enthalpy, but then we also had entropy, and we did have this idea of free energy. So I'm just going to quickly go through that again. You haven't got a print off of this one. I didn't particularly want you to have this information. It's not, it's not very thorough, really. It was, as I said down there, a very brief overview. But when we get to the last slide on this, I realise it tips directly into what I want to do this afternoon. So I could have made it one big thing, but yeah, I didn't. This idea of thermodynamics, movement of heat, the thermo bit suggests heat. It's not always heat, but it is energy. And the movement of energy, we were quite clear on that in the energetics section, but it's not necessarily so clear in redox. But you've got to remember, electrons equals energy, doesn't it? So we are talking about the movement of energy. You can have a mole of electrons and they will have a certain amount of energy. We'll be back to that one. All right. So when we look at the number of electrons, and with most of our metals, you know, we had these equations with 2e minus in there. Well, that represents 2 moles of electrons. For every mole of metal that's involved, you're having 2 moles of electrons involved, and they represent a certain amount of energy. So that's where this all joins up. I did suggest that, you know, if you were sort of really interested in how this all linked up, then have a look at Khan Academy. It's not just one of those YouTube videos where they write it all out and everything. There are actual sort of sections in it that explained it quite thoroughly, and it's a good, reliable source. So, you know, have a look at that if it's something you need. The first board, yeah, another one of my don't do it like this PowerPoint slides. Way too many lines on there, but because I wanted to get all the laws of thermodynamics on one slide, that's what I did. Please don't try and do that on your biology ones. You know, they say 7 lines should be your maximum. Sometimes you might need to go over, but don't write out full sentences and things. But this was just describing the laws of thermodynamics. Not too concerned about those this afternoon. This was quite important, though, this idea of a system. What do we mean by a system? It's matter, and, well, you can describe it, once we've got this matter, in terms of composition, pressure, volume, temperature. And then we had 3 options: isolated, closed, and open. Right, so those will, you know, they will be more relevant as we go along. So isolated, you can't gain or lose matter or energy. Closed, you can gain or lose energy, so, you know, you could have heat perhaps transferred in or out, but not matter. And open, yeah, well, that's biological systems are open, aren't they? We worked through very superficially this idea of internal energy in a system, and then it started to get really quite messy. But we were looking at that concept of enthalpy that we've been working with, and the idea of the internal energy, and we got, yeah, some other ways of looking at the idea that the enthalpy, this energy that we've been measuring, was partly the internal energy, but partly to do with pressure and volume. We sidetracked a little onto entropy. Well, it wasn't a sidetrack, but it was an important thing. Entropy is a measure of disorder. So, for example, a gas has a higher entropy than a liquid has a higher entropy than a solid. You know, it's that sort of thing. And a teenager's bedroom has the maximum entropy possible, I think. All right, so this measure of disorder. We introduced all sorts of things like multiplying it by temperature gives you a measure of the heat present. And we ended up with this idea of free energy. Now, the free energy, this Gibbs free energy, is literally where I'm going on to at the beginning of this bit. So this is why it was worth looking at. And that formula there, delta G equals delta H minus T delta S, you will see is practically, yes, the first thing, well, one of the first things on the first slide that we're going to look at in a minute. So I will put this onto Moodle so that you can have a look back at it, and if you want, you know, to get a better understanding of it, that's then up to you. You don't need a huge amount of explanation of all this. But what this free energy is, it's the energy that is sort of available to do something. And we call it doing work. The energy is available to do work. It's not energy, you know, that's been perhaps used to create chemical bonds. But it's going to be our starting point for this one. Right, this is the one that I've given you now. And most years I talk through this, write notes. But this year I thought, right, let's make this a little bit quicker so we can try and do it this afternoon. And then, you know, if you need more information, you can ask me. You can go and research it, and then, you know, launch you into the assignment and see how you get on, basically. So this is where we're looking at feasibility. which is to do with electrode potentials, the Gibbs free energy bit of it as well, but also going into equilibrium constant, so it overlaps with the last learning outcome as well. And we start with the Gibbs free energy bit, and you'll see some of these slides have got the most ridiculous amount on them, but I couldn't actually split it over slides because you needed the sort of continuity with it. So yeah, what you find, the slides on your handouts go left, right, and then you turn it bottom to top, and it goes left, right again, I think. All right, this first bit, there's a couple of slides that introduce Gibbs free energy. Then we've got 1, 2, 3 actually on some calculations relating to electrode potentials. And then there's a couple at the end that relate electrode potentials to equilibrium constants. And there are numbers in there, and I thought it was just easier to do it like this and have me writing the numbers on the board, making mistakes in them, and yeah, hopefully this will make it a bit clearer. Oh, it's just a bit, not clearer necessarily, it's just that bit sharper and more organised. Okay, this idea then of least free energy or available energy does relate to entropy, this measure of disorder. The more entropy, the higher the entropy, the less free energy there is. You know, everything's just distributed evenly throughout the space there is, and that's that. You know, it's the lowest state of entropy, or it's the lowest amount of energy. Sorry. And this common expression here is not one we're going to be able to use because you're not measuring any of these things. All right, because what you're going to do, you're going to calculate Gibbs free energy based on electrode potentials. There's no electrode potentials in here, but this is the pickup from the other PowerPoint. So delta G being delta H minus T delta S, all right? Enthalpy, temperature, entropy. We can't measure the entropy, so we're going to have to use a different route. What we're looking at, though, this idea of feasibility of a reaction is about, will it happen spontaneously for a start? And if it will, you know, which way out of an equilibrium is going to happen? And the idea of a spontaneous reaction, then, we have 3 options with delta G. It can be positive, negative, or 0. Now, in order for a reaction to happen without us doing anything to it, you've got to have a negative value of delta G. And I've put on here most likely at higher temperatures, and if you think about this, the bigger that number is there, the more likely you are when you take it off that to have a negative number, aren't you? So higher temperatures, and also at increasing achievement of disorder, in other words, higher values for delta S. So the bigger this term is, the more likely that is to be negative. All right, now this isn't a particularly useful definition for us in terms of using electrode potentials. So yeah, we're going to take a different approach to this. But it would be things like, and I've given you a couple of examples here, melting ice, where you go from solid to liquid. You could say boiling water to become water vapor. You know, those are going to happen spontaneously. But your delta G will be negative for those. Another one, actually your boiling water isn't, because you're going to have to put a lot of heat into that, but melting ice at room temperature, this is the problem, isn't it? Metal plus acid, I thought was quite a good one, because what state is the metal going to be in? As a solid, yeah. The acid is, well, it's a liquid, it's an aqueous solution, isn't it? So it's a liquid. So we've got a certain amount of entropy, a certain amount of disorder on that side, a solid, which is actually the most organised state, and a solution, which is fairly disorganised. What have we got on the other side? The salt will be, it'll actually be in a solution, won't it? Because we can't get the acid to react without it being in a solution. But hydrogen is a gas, which is the most disorganised state to be in. So that will happen because we've got this increase in entropy. Right? We go to greater disorder if we're going from left to right there. Does that make sense? All right, that solid plus solution, or liquid if you like, giving liquid plus gas is an increase in entropy. So we don't have any problem getting metals and acids to react together. All right, so it's you know, just a simple example, really, to sort of show you something that you're familiar with. So we have this idea then that a reaction will happen spontaneously if delta G is negative, you know, and that is this increasing term here. But you've got three options. Let's just move that out of the way. If it's negative, energy is going to be released, and that means that the system can do work, and it's ending up with energy being given out. What you're left with has less energy. That takes us back to the idea of enthalpy, doesn't it? The endothermic, exothermic, all that. Well, I don't want to go back to that learning outcome and confuse matters. If delta G is positive, work has to be done on the system to make the reaction occur. Well, that top one would probably be then your endo or exothermic. Exo. The second one would be endothermic. If delta G is 0, the system's at equilibrium. Oh, we've done plenty of those equilibria things in the last learning outcomes. It just sits there. You know, it's going equally both ways. Probably the energy released from the system is enough to go back in and keep it working. So it's balancing itself, because remember, equilibrium is the two reactions in an equilibrium going equally in each direction. And of course, you know, we had this idea that for endo and exothermic, a reaction in one direction might be exothermic, but the reaction in the other direction would be endothermic. And so if you reach equilibrium, of course, you've still got an endo and exothermic reaction going on, but one is feeding the other. So if we can calculate delta G, then you can predict whether a reaction's feasible or not. Now, we use rather silly examples because the reactions you're going to do are quite obviously feasible. They happen. But, you know, to predict the feasibility of a reaction that you don't have the practical means to carry out could be quite useful. So how can we do this then with electrode potentials? This is the next bit then, because this is where we can actually use the readings from, I don't know if you can use, no, you can't use the readings from your practical, but you can definitely use values out of the data book. So, you know, you've got these values for the electrode potential, which are, you know, they're just numbers, they're voltages, comparing the position of equilibrium in a metal with the position of equilibrium in hydrogen, you know, using the electrode setup. But you can also define it as a measure of the maximum amount of energy per unit charge. Unit charge, you've got the electrons. They're negatively charged. So how much energy is in each one of those? That's available to do work when charge is transferred through an external circuit. All right, so that's a bit of a definition there. And what it really means, that the overview of that is that it's a measure of the energy that you actually got available when you have this redox system set up. So you've got an overall redox reaction for a cell that's made of two half cells, and you know how much energy is available. Well, what daily application does that have? Batteries, yeah. So, you know, I have in the thing on my belt a 9-volt battery. So, you know, that's coming from, you know, that idea of the energy it can give to power the microphone and everything is really all down to this, isn't it? So it's the energy you can get from that circuit. And some things can be set up to create batteries, you know, some different sorts of electrodes and equilibria can, and others can't, you know, because there's not enough energy coming out of the overall redox reaction. But if we can measure that, then we've, this maximum work that we could have, theoretically, is equal to the change in Gibbs free energy in the reaction. Now, you know, you don't buy your batteries based on the amount of Gibbs free energy that's available. You know, you just want to know, will it work? But you can do this calculation for the cells that we're going to set up. So this is I think it's 3.3. I think it's calculating this. I'm not sure. Now, up at the top there on that slide, this one is not the most packed one. It's the next one that got out of control, but that was because it's got all the calculation on it. Couldn't do it any other way. The relationship between the electrode potential, well, this is actually the overall cell potential, the standard cell potential, and Gibbs free energy can be expressed like that. So delta G naught equals minus N F, we haven't met F before, that's a new one, E naught for the cell. Right, E naught for the cell is what you're measuring. I would, however, suggest that when you do the calculations on the assignment, you don't use the ones that you got in class. Or if you use those, say, because we know they're so way off the theoretical ones, lots of them, that it actually doesn't matter which ones you use, but I think I'd use the theoretical ones from the book. This is only a matter of demonstrating you can do this. Right, just going to tidy that up on the screen a bit. When I copied and pasted here, some of the word spacing, oh no, it did have to fit there, but there were gaps. I know you haven't got the tidied up version of it. Right, don't think I can do it with that one, won't have enough space. Okay, what have we got? Those component parts, we've actually got enough information to do this now. Well, you will have. N is the number of moles of electrons transferred per mole of ions. You should be able to already tell me what we've got for that. How many moles of electrons are we going to have involved with each mole of ions? What are your equations? For the magnesium electrode, it is Mg2 plus, that's 1 mole of magnesium ions, plus 2 E minus. So how many moles of electrons per mole of ions? 2. Yeah? Each mole of magnesium ions is involved with 2 moles of electrons, isn't it? Because it's a 2 plus ion. So throughout all your calculations, N will be 2. Don't forget the minus. F is another fiddle factor. It's the Faraday constant. And that is, that's not very tidy either, 9.648533 times 10 to the power 4 C. Right, it is C per mole. All right, I thought I'd gone through this and tidied that up. Have you got it on one line? No. It was because I was doing it at about 6:30 this morning. I suddenly decided this would be a good idea. But yeah, I went through and tidied some bits up. But yeah, that moles to the minus 1 should be next to the C over there. C down here, uppercase C, is a unit called a coulomb. Anybody seen that in this room anywhere? Anybody seen it in this room anywhere? Sure, I'm hoping it's over there now. I've pointed to it. Yes. I thought it was on there. I was absolutely certain it was on my list. No, it's a derived unit, that's why. That's the problem. Sure, it was an SI unit. Okay. Right. You were right. Yes, you hadn't seen it. Coulombs. Strange word, but coulombs per mole. It's the amount of electric charge carried by a mole of electrons. All right, so 1 mole of electrons will carry 9.648533 times 10 to the 4 coulombs of charge. All right, now we know, we're multiplying that. So what we're getting there, N times F is giving us the total amount of charge in the electrons that we are transferring about. The minus is another matter. The E naught for the cell, the standard electrode potential, standard cell potential, is what you're either going to measure or calculate from the book, and it doesn't matter which you use, as long as you say which you're using. That's fine. You will be coming out with, I think, what you get out of that. No, it doesn't matter anyway. But that's what you're going to use. All right, that's why I've done it in bold. You will need to calculate delta G naught from minus NF E naught for the cell. Now, what I said earlier on, the previous slide said, in order for a spontaneous reaction, we're going to need a negative delta G. If it was positive, it wouldn't happen, not without putting some energy in. And if it was zero, it'd be at equilibrium. So if we're going to have a spontaneous reaction, we've got to have a delta G naught less than zero. And in that case, we must end up with a positive value for our cell potential, which you will. The way to work it out, which I hadn't put anywhere else, I just realised I hadn't used the words anode and cathode. One of the reasons for that is I get confused over it because the definitions of current flow and movement of electrons and all that sort of thing between chemistry and physics are different. But in this context, in the redox context, it's just easy then to actually refer to them like this. So at the anode, you've got oxidation. Now, oxidation is loss of electrons. Yeah. So the one that's giving up its electrons most readily, that's the one with the most negative electrode potential, is going to be the anode. Cathode is reduction. Reduction is gain. So that's the one with the least negative electrode potential. Okay. So that's how you work out your cell potential. We'd sort of done it yesterday just by saying the difference between the two half cells, haven't we? It's a bit cheaty, but yeah, that's how you get the right answer anyway. All right. So oxidation is loss of electrons. Reduction is gain. Yeah. Okay, that doesn't leave us very much. Now, this was where it got really messy, and I thought, honestly, I really ought to try and get this onto 2 slides, and then decided, no, it wasn't going to happen, and ended up squashing it all onto this one. So, sorry about this. I'm going to have to move bits around as we go. If you need to sort of rewrite this, but like I say, this will go onto Moodle. So if you want a full screen, full page version of it, you can get it. So if you've got a cell, oh, I like that. For a cell where zinc and copper form the electrodes, can you spot the mistake? Yeah, then I've put lead in. The reason was my original idea was to do zinc and copper, and then realised that was one that was in the assignment. So it should at the top say, for a cell where zinc and lead form the electrodes, we've got these two. I should have done those as equilibria, shouldn't I, really? Right, we've got a zinc and a lead equilibrium. We've got our electrode potential values over on the right-hand side. The lead is the cathode because it's gaining electrons. That's the reduction side of it. The zinc is the anode because it's losing electrons. That's the one with the more negative electrode potential. So if we work out our overall cell potential as get this the right way around, the cathode minus the anode, all right, we end up with 0.63 volts. So that's the cell potential. If you were to wire those up as 2 half cells, like we've been talking about, like you're going to set up later, but obviously we do have this problem with lead salts not being soluble on the whole. That's the value that you would hope to see on your voltmeter. That's the cell potential. That's what you're measuring. And we've got 2 moles of electrons transferred per mole of reactants in both cases. And that's one of the things that's made this a bit tricky, because trying to find an alternative metal to magnesium, because of the problems we know it's going to introduce, I was left with other options, one of which was aluminium, but aluminium forms 3+ ions. And so we would have one of our electrodes doing 2, the other doing 3. So yeah, we'd have that need to multiply them up to get to 6. And it was going to potentially cause a lot of issues in the calculations. So yeah, we'll just see what the magnesium does. Now, one thing I haven't mentioned so far is, we've been talking about volts. We've been talking about measuring volts on the multimeters and things. But what's a volt? I said it's a sort of measure of the difference in pressure, if you like, pressure of electrons, so that, is it more likely to move that way or that way? And if the pressure of electrons is greater over here, it'll move that way, that sort of thing. That's what voltage sort of measures. That's a real biologist's way of describing it. But you find that there's an awful lot of circular definition in science that we already met this with Gibbs free energy. Could be defined in two ways. You've got that delta G equals delta H minus T delta S, but delta G also equals minus NF E naught, right? So you can keep sort of redefining. You can almost substitute one definition into another and end up with something completely different. A volt can be defined in various ways. And a really useful way that involves a relationship between energy and charge. We measure energy in joules, and of course also kilojoules, but do make sure we're talking about joules here, and very often values in the book are about kilojoules and all that. You've got to make sure you're using the right sized units. We've got this idea that you can measure, the charge carried by 1 mole of electrons. Fine, measure that in coulombs. But the definition of a volt includes this. It's the potential difference between 2 points. That's the pressure difference, if you like. That will impart 1 joule of energy per coulomb of charge. Aha! So that means that 1 volt equals 1 joule per coulomb. So if we can measure the number of coulombs of charge that we've got, we can convert that directly into joules. We can get the energy out. If we know the volts, we know the coulombs, there you go. All right. So let's get rid of that up there. So if we use that delta G equals minus NF E naught for the cell, we get this. Delta G naught for that example up there is minus 2, because that's the minus 2n, multiplied by the Faraday constant. Really important in something like this to keep putting the units in. But oh dear, you can trip over that so easily, getting the uppercase, lowercase thing wrong. So we've got that many coulombs per mole. I've lost the decimal places. Because, it was times 10 to the 4, 9.7 times 10 to the 4. So that's actually written out fully. Multiplied by the 0.63 joules per coulomb. Where's that 0.63 from? Up here. All right, 0.63 volts, because a volt is the same as a joule per coulomb. So we can now have something which will cancel out. If we multiply coulombs by per coulomb, we lose them, don't we? So what are we left with? Joules per mole. Oh, that's handy. We're familiar with that, aren't we? Energy values. Think of all that enthalpy stuff. It's all in joules per mole. And that's what we end up with. But it wasn't in joules per mole, was it? It was in kilojoules per mole. Yeah. Be careful, because what you'll end up with to start with here, you'll get joules per mole, but convert it to kilojoules per mole. That's fine. And what you end up with for this particular one is a negative result. Doesn't matter how big it is, actually, but as long as it's negative, it's feasible. There you go. That's all there is to it. Simple. I can't believe I said that. If you try to make it go the other way, because remember we are talking about equilibria, but we've already worked through this idea that the equilibrium for the zinc would be further to the left than the equilibrium for the lead and all that. But we can now prove it really in terms of Gibbs free energy, because if you tried to reverse it, of course, you would have the same sized Gibbs free energy, change in. So you'd have the same number, delta G, but it'd be a positive number. So it wouldn't happen. And so it's not a feasible reaction for this to go the other way. So it's feasible for zinc to become zinc ions and lead ions to become lead, but not the other way round if you put the two together. So, you know, this is just sort of confirming. If you're thinking this is new, it's not. This is confirming what we've already been talking about. Okay, what does that leave us with? The last bit. We've nearly finished chemistry. Okay, now, different topic here, and only 2 slides on it. But it's, again, it's just to bring a little loop back to the last learning outcome. Free energy change can be related to the equilibrium constant. This time, delta G equals, delta G equals all sorts of things, doesn't it? Minus RT, natural log of Kc, and Kc is the thing we want to work out. R we've met before, the gas constant, yeah? 8.3145 joules, not kilojoules, per Kelvin. This is a bit of a pain because we've got a capital K there, we've got a capital K there. For goodness sake, get them right. I think this particular section is more of a test in getting all your units right than anything else. Calculations are quite straightforward. You stick the numbers in your calculator, job done. Writing it out with the right units in the right place, using the right conventions, not so easy. So, our gas constant, joules per Kelvin per mole, and then temperature, if you know we don't have any other information, 298K, but we should do for this afternoon, shouldn't we? So it could, you know, if you're using the lab results, then you'll need to use this afternoon's temperature. Right, example. We met natural logs last time, so we know that natural log is the inverse of, yeah, E. It's when you're doing E to the power of something. You're in, you know, logs and indices, powers, if you like, are the inverse, aren't they? Yes, they are, is the answer to that. You might have to look back at the last assignment to get your head around the logs again. But, you know, you think you're never going to need them, and then they pop up in 2 assignments. If we took that zinc lead cell that we just calculated through for, you've got the value came out. You've got 2 options. It was either minus 121571 if you did it in joules, all right, or 121.571 if you did it in kilojoules. So again, it's just feed the numbers in, rearrange it. You get the natural log of Kc coming out of 49.1. I said ish because I just, yeah, there's a limit to how many decimal places you need here. To get the value of Kc from that, all right, because if the log of Kc is 49, then Kc is e to the power of that. So again, you've got this on the slide. You only need to feed your numbers in. You don't even have to understand how this works. You literally put your numbers in there. Make sure they're the same. All right. You literally put your numbers in. Make sure they are the same order of size. So when you check with this, if you've put in 121, you know, if your number is in the hundreds that you put in, no, you need to put it in joules. And you get, yes, some rather ridiculously sized numbers, don't you? And we had a quick look at Stevens yesterday. One of the answers came out times 10 to the power 92, I think, didn't it? What we're looking at is an equilibrium constant. So think back to the last learning outcome. What's an equilibrium constant? Here is the equilibrium constant for that cell. Product over reactant. Okay? Concentration of the product, concentration of the reactant. Because the zinc was going to become zinc ions, the lead ions were going to become lead. So, you know, in terms of the direction that that went, that would be our overall reaction. I don't think that was written anywhere in all of this. What this means is that Kc is that huge number. That means that the top of this expression here is that much bigger, or that many times bigger than the bottom. So it means that you've got a vast amount more product than you have reactant at equilibrium. Pretty much all of it. In other words, you pretty much lose all the reactant and everything turns into product. So the size of the equilibrium constant here is just telling us that this pretty much goes to completion. So yeah, this high value of Kc means it goes effectively to completion, leaving virtually no detectable lead ions in contact with the metallic zinc. If that's, yeah, if it was a, yeah, if you're setting it up like a battery, which we're not. Okay, I think that is job done in terms of the theory content of this unit.